Hello friends, today we will be discussing an experiment of Newton's ring. The aim of the experiment is to determine the wavelength of sodium light by Newton's ring method. The apparatus will require here is optical arrangements for Newton's ring, a plano-convex lens of large radius of curvature, two plain glass plates, sodium lamp and a travelling microscope. This is the pattern we observe in Newton's ring. Newton's ring is a special case of interference at wedge-shaped film in which an air film is formed between the glass plate and the convex surface of the lens. So when a plano-convex lens of large focal length is placed on a plain glass plate, a thin film of air is formed between the two surfaces in between. So when a monochromatic light falls on this film, the light reflected from the upper and lower surfaces of the air film interfere and we get an inner dark spot surrounded by alternate bright and dark rings. They are known as Newton's ring as Newton's observed it first. Now let us see what is interference of light. So when two light waves of similar frequency having zero or constant phase difference propagate in a medium simultaneously in the same direction, then due to their superposition, redistribution of energy takes place. So as a result, at some places maximum intensity or bright fringe is formed, which is due to constructive interference, whereas at some other places minimum intensity or dark fringe is formed, which is due to the destructive interference. So the phenomena of redistribution of energy due to superposition of waves is called interference of light waves. Now let us see what are the conditions for constructive interference. The phase difference for it should be 2n pi and the path difference should be integral multiple of lambda. The amplitude of the resultant wave at this moment is a plus b, where a and b are the amplitude of interfering waves. For destructive interference, the phase difference should be odd integral multiple of pi and path difference 2n minus 1 lambda by 2. The amplitude of resultant wave becomes a minus b. So if the interfering waves are of same amplitude, the contrast is good. The formula of wavelength of light, after customizing it for our this situation, becomes lambda is equal to dn plus m square minus dn square upon 4 mr, where dn plus m is the diameter of n plus mth ring, dn is the diameter of nth ring, where m is an integer number which can be considered anything like 2, 4, 3, anything. R is the radius of curvature of plano-convex lens, which can be determined by a spherometer by relation R is equal to L square upon 6h plus h by 2, where L is the distance between the two legs of the spherometer and h is the height of the convex center of the convex lens. This is the set of the Newton's ring. This is a sodium lamp, the monochromatic source, and by a slit the light is coming out. So to ensure that a parallel beam is falling on this glass plate, we place a lens. So this is a plain glass plate kept at 45 degrees, so that the angle of incidence is 45 and again angle of reflection becomes 45, and they fall normally on the plano on the arrangement. So then this is reflected back. So we can see an air film here on the other side, right hand side of it. We can see that air film is formed between the plano-convex lens and the plain glass plate. So light which falls at this surface, so the rays which you can see here as 1 and 2, they interfere and produce the interference or the Newton's rings. This is the experimental setup for Newton's ring experiment. This is a tube in which a source of monochromatic light, the sodium, is fixed. In this tube we have a convex lens to provide us a parallel set of beam to fall on the arrangement. Here this is the screw gauge This is a telescope, and this is the focusing knob. With the help of this knob, we can focus our system on the rings properly. Now let us have a look at the arrangement here. Light falls on a plain glass plate which is fixed at an angle of 45 degrees. This is the plain glass plate. We have a plano convex lens. This is a plane, one side is plane and other is convex. This is again a plain glass plate. So first we place the plain glass plate, and over this we place the convex side of the plano convex lens so that a film is formed between the two. When a parallel beam of monochromatic light falls on the glass plate fitted at 45 degrees, it bends it so that it falls normally on the arrangement, and which reflects it back, received by the objective of the telescope, and then can be seen from the eyepiece. From here we can see the Newton's rings. We take the readings with the help of the micrometer screw fitted alongside with the telescope, and this is the micrometer screw, this is the reference line, and this is the circular scale on which we have divisions up to 100. Now let us see how to take readings with this. So first of all, we'll find out the least count of this instrument, and then to take the main scale reading, we'll see that whichever division of the main scale is coinciding with the circular scale. For example, in this case, 11th division is just before on the circular scale, so this is will be 11 millimeter will be main scale reading. Then the division on the circular scale which is coinciding with the reference line, for example 39 in this case, will be multiplied with the least count and will be added to the main scale reading. That will be our total observed reading. So to start with, this is the pattern of the Newton's ring. We take our telescope to left end and then focus it there on the, suppose say 20th ring, take the readings and then move towards the right side, take the reading for that ring, for example 18th and then 16th and so on. Then we take it after we go to the second ring, say, then we move towards the right end for the second ring on the other side and take the readings. Then when this reading will be subtracted from this reading, that will give us the radius diameter of that particular ring. Similarly, reading subtracted from this to the other end, that will be the diameter of that ring. So in this way we go on subtracting the values and get the diameter of that particular ring. Now let us see how do we interpret our result here. So first of all, we'll note down the least count of the microscope, and this is the table for the determination of diameter. As I told you, we take it to the left end and then take the micrometer reading for say 20th ring, then for the 18th ring, and this way we keep on moving towards the right hand side and take the readings for 18th, then 16th, 14th, 12th and so on for 4th or second ring. Then we go to the right hand side of this 4th ring, say in this case, and then again keep on moving to the right side and take the reading for the 20th, the right hand of the 20th ring, right end of the right. So when we this subtract A to B, the difference of A and B will give the diameter of that particular ring. So in this way we will find out the diameter of almost all the rings. Then we choose any number M, say 4. So we'll subtract the reading of 16th ring from 20th ring and get the dn plus m square minus dn square, and so on from 10th to 14th and 8th to 12th, and so on. We will get the diameters. So the wavelength of the sodium light is given by lambda is equal to dn plus m whole square minus dn square upon 4mr, where r is the radius of curvature of plano-convex lens and can be found using spherometer. Now these values of r and dn plus m square minus d square will be substituted in the formula, and the result is reported in angstrom unit. This difference of the squares can also be obtained from the graph as shown. The graph is plotted for the number of rings versus d square. We can take any value of m and then find out the difference as shown in the graph to get dn plus m square minus dn square. Substitute the value in the formula and we can get the value of lambda. So we can report our results as the mean wavelength of sodium light is obtained by this much, standard value is this much, and so on. So let us discuss the precautions we have to follow. First of all, the glass plates and the lens, they should be cleaned thoroughly, and then plano convex lens used should be of large radius of curvature so that we get a thin film, and the source of light should be monochromatic. Before measuring the diameter of the rings, the range of the microscope should be properly adjusted and the least count should be properly found. The traveling microscope should move only in one direction to avoid backlash error. The crosswire should be focused on a bright ring tangentially. The radius of the curvature should be measured accurately. So we must follow these precautions to avoid any error. That's all about the experiment. Thanks for watching and have a nice day.